Alright, on this question, Bill and Eric are heading out of town. Heading out to the next town, I should read this, along their trip. Eric has some errands to attend to before he can leave. Bill's speed is 50 miles per hour, and Eric leaves 30 minutes later, rushing to catch up at 55 miles per hour. That's not really a rush, in my opinion, but whatever. How long does it take for Eric to catch up, and how far have each of them gone before he catches up? So we have two people traveling at a set speed for a certain amount of time, so this is definitely a uniform motion problem. So I'm going to write down my formula, distance equals rate times time. And I'm actually going to set up my chart because I'm recognizing, again, there's two different people. That means there's several different variables to keep track of. So I'm going to do rate, time, and distance here. And I'll say Bill and Eric. All right. Now I'll read through this question one more time, this time filling in the numbers as I come across them. Let's see, yada yada yada. Bill's speed is 50 miles per hour, so Bill's rate is 50. Eric leaves 30 minutes later. That's not really the time that either of them are traveling, so I'm not going to write that down. His speed is 55 miles per hour. Okay, we do know that. How long does it take for him to catch up? Okay, so there's a bunch of unknowns here. We don't yet have enough information to use the fact that rate times time equals distance. We need to somehow introduce some sort of variable here. Now, the things I'm actually looking for, it would be nice to know how long each of them have been traveling. So I'm going to go ahead and call this x and this y, because then I can say the distance here is 50x and the distance here is 55y. Okay, so I now have I have these equations filled in, rate times time equals distance, which means I have some expressions I can refer to the time Bill has been traveling, the time Eric has been traveling, and their distances. Well, I know that if Eric has caught up to Bill, then they must have been traveling the same amount of distance, because if they're starting at the same point and they end at the same point, regardless of when Eric took off, if he's catching up, they would have traveled the same distance. So that means that 50x, that's supposed to be 50, that means that 50x must be equal to 55y. But because I've introduced a second variable here, I need to have a second equation. And the only thing I haven't really used here is the fact that Eric leaves 30 minutes later, 30 minutes after Bill. So that means that ultimately he's been traveling for 30 minutes less. Now, I do have to be careful here. I didn't mention it before, but when I write rate times time equals distance, I need to make sure the units work out. And the speed is in miles per hour. So it makes sense that the distance would have to be in miles and the time would have to be in hours. So that when I go to modify x and y, I want to make sure that this is also in hours. I'm going to call this 0.5 hours instead of 30 minutes, because I don't want to say it's minus 30 hours. I want to say it's minus 30 minutes, or 0.5 hours. All right, so the time Eric has been traveling is 30 minutes less than the time Bill has been traveling. So however long Bill has been traveling is, you could say, is y plus 0.5. You could do it this way, or you could say x minus 0.5 equals y. I'm choosing to write it this way because I like having the plus in there. It just makes my life a little easier, not having to deal with subtraction. So whatever the time Bill has been traveling is, I can find that by figuring out how long Eric is traveling and adding a half hour to that. So that's what this equation is saying. Okay, so I've set up my system of equations. I can kind of scoot this down because I don't need to look at the problem up there anymore, because I've now set up, I have two equations for my two unknowns, and, well, I can actually see what my unknowns represent right here. The fact that I wrote x in this box means that x represents the time Bill has been traveling, y represents the time Eric has been traveling. All right, so in this problem, let's see, I'm thinking substitution is going to be the way to go, because this x is already, or this second equation is already solved for x, which means that this value can take the place of x in the other equation. So I'll do that substitution. I get 50 times x, but x is now y plus 0.5 equals 55y. Alright, well, this equation I can solve. Notice there's only y's in here. This is the whole point of these substitution and elimination methods. It's to figure out how to combine these two equations into one, such that you only have one variable. So distributing my 50 through here, I get 50y plus 25 equals 55y. It looks like I'll subtract 50y from both sides. I'm choosing to move this, get this term over onto the other side of the equation since I have a constant here already. I mean, I could subtract the 25 from both sides and then subtract 55y from both sides to get rid of this term and that term, but it's actually quicker to just move it this way. I get 25 equals 5y. Then to finish solving this, I divide both sides by 5, giving me y equals 5. Alright, so y is the time that Eric has been traveling. Let's look back up at the question. We're being asked to figure out how long does it take for Eric to catch up, and so actually the y is exactly what we're looking for. We're looking for how long it takes Eric to travel, how long Eric has been traveling to catch up. So I'm going to go ahead and say y is 5. That's my answer. That's 5 hours. The follow-up there was how far have they each traveled to catch up. How far have they each traveled? Well, I might do this in two different ways. I might say if Eric has been traveling for 5 hours, that means Bill has been traveling for, well, 5 plus 0.5. This is kind of dragging. X equals y plus 0.5. That's this equation right there. So I get 5 plus 0.5, or 5.5 hours. So Eric has been traveling for whoever the first person is, has been traveling for 5.5 hours. And their total distance would then be 5.5 times 50, because it's traveling at 50 miles per hour. So let's figure out what that distance is. 5.5 times 50 gives me 275 miles. If I wanted to double check this, I could say, so this is the time, I should probably actually read this since that's Bill. This is Bill's distance. If I wanted to verify that their distances are the same, I could say what Eric's distance is. This would be distance equals rate times time. Distance equals, let's see, he's traveling at 55 miles per hour, and he's traveling for 5 hours. 55 times 5 gives us 275 as well. So you can see they've both been traveling for 275 miles. It's nice to kind of do this and verify that things work out. But there's the first part of the question, and there's the second part of the question. It took him 5 hours to catch up, and they traveled a total distance of 275 miles.